Everyone. So this video will see the geometrical meaning of the dot product basically in R3. So in R3, dot product is a algebraic concept, but in R3 it has a geometrical meaning. So we see here that geometrical meaning, and that concept we actually use in R4 or R5 in general for any inner product space. Okay. So let me write down here the definition for dot product in R3. So let two vector we take it. So let's say u vector is, I'm writing that a1 I cap plus a2 j cap plus a3 k cap, and let b vector equal to b1 I cap plus b2 j cap plus b3 k cap. So now the dot product actually defined algebraically this way, that u dot v. Sometimes people write in this form, this way. But most of the time in this lecture we use this actually u dot v, the second notation. So this is how defined. This is basically a1 b1 plus a2 b2 plus a3 b3. So dot product totally defined algebraically so far, because the product and addition we have used. These are the component. A1, AIs and PIs are the component of the vector U respectively. Then dot product basically defined this way. Now we'll see some property of the dot product. So let me list here property of dot product. Very important property. You can check directly. I'm not going to the proof of those. Just I am writing here the property, that the number one property is basically that if you take dot product of u with v, then it is same as v with u. And then second, if you take dot product u dot e plus w, it is same as. Sometime we call it is the distributive u dot v plus u dot w. And then third, if we take a scalar c of u vector dot e vector is equal to u vector dot c of e vector is equal to c of u vector dot e vector. So u vector dot e vector. And then fourth is this, that u vector dot u vector, it is of course greater than 0 for all u vector not equal to 0 vector. So this dot product actually algebraically defined this way. I call it is a star. This is the definition of dot product. Now dot product has this following four property. All theorem related to dot product can be proved using this four property most of the time. Now see, so far we defined dot product algebraically, but it has a geometrical meaning that we are going to discuss now. Okay. So see, if we take any vector in R3, it is nothing but a directed line sequence. It starts from the initial line and it will terminate at the terminal. It will start from the initial point and it will terminate at the terminal point. So for convenience, we will take initial point for all vector 0. Okay. So every vector started from 0. So that means 0, 0 from the point 0, 0. So let me write down here that this is our actually the 0. So let me define here, this is 0, and let me put here our u vector is this. Okay, and let's say this is our v vector basically. So let's say this is a point, this is b point. UV, of course, the previous vector. It is given here. U vector having component a1, a2, a3, v vector having component b1, b2, b3. Now, of course, then we can create this vector a to b. This vector basically from here to here. See, by sum of triangle law, of vector, we get, so clearly OA vector plus AB vector equal to nothing but OB vector. So O to A plus A to B is the same as O to B. So from here we can write AB vector is nothing but OB vector minus OA vector. So now see, OB vector is nothing but, so AB vector equal to, OB vector is the B vector and this is nothing but U vector. Now see, AB vector equal to 1. So one thing here important, in R3, what we can do basically, in R3 we can create a triangle. Okay, but in general, for arbitrary vector space, such triangle we cannot draw explicitly. We can imagine such situation can occur there, but explicit triangle we cannot draw for R4 and R5. Up to R3, in R2 and R3 we can draw the triangles. So that's why this picture only valid for R3 and R2. So therefore the work I am going to do here, it's valid for only R2 or R3. Okay, this one basically. So now this is actually what? So this is basically, you put here v vector is it is what? B1, B2, B3 component. So it will be B1 minus A1 of I cap plus B2 minus A2 of J cap plus B3 minus A3 of K cap. So AB vector is this. Okay, fine. So we have a triangle and we know AB vector, OA vector, OB vector. Now suppose the middle angle. So I'm now considering here. Let theta is the middle angle. Is the middle angle between, so between u vectors and p vectors. So where I am taking this convenience, theta is in between 0 to pi. So okay, so basically I'm taking here that this is less than pi. Okay. So now this angle is theta. Okay. Now see, we have a triangle OAB. This angle is theta, and we know this length. We know this length. Also, we know this length. Now let me recall you the cosine law for triangle. So cosine law. So let me use the different color. So cosine law for triangle. So cosine law for triangle. Actually, this law actually is true if you have a triangle. Okay. Now let me state here. If you have a triangle, let's say this length is called A, B, and C. This is C, this is A, this is B. If this angle is, let's say, theta, or whatever. So there are three laws basically. Okay, I'm doing for just taking this theta. So then the C square equal to, I mean this length square equal to A square plus B square. Okay, minus 2AB cos of theta. So middle angle. So if you have a triangle, if you can draw a triangle, and if you know the angle between two sides, then other sides square equal to the sum of two sides square minus 2 into two sides product into cos of the middle angle. This is the cosine law for triangle. Now let's use this cosine law for here. So in this situation, you know, this angle is given theta. So now AB length, the length of AB is nothing but, if we use by cosine law, we get by cosine law, we get that that AB, this vector, what was it? It was basically yes. The AB vector norm whole square, this means the length of AB sides, equal to OA vector length square, okay, plus OB vector length square, right? And then minus 2 into OA vector length, OB vector length, and cos of middle angle. So this is nothing but cos of theta. Theta is the middle angle. Now we put everything here. So what will be the norm of AB? AB vector we know has component this, and this. So we'll get here basically, if we put, then we'll get B1 minus A1 whole square plus B2 minus A2 whole square plus B3 minus A3 whole square. Because AB vector is this, which component are B1 minus A1, B2 minus A2, B3 minus A3. So you know the norm square is nothing but, you just remove the square root from the formula. So just it is the square of the sum of the square of the component. So now OA square will be what? This is nothing but A1 square plus A2 square plus A3 square. Now OB square will be B1 square plus B2 square plus B3 square minus the norm of OA vector is nothing but norm of U vector, right? And norm of OB vector is nothing but norm of E vector, okay? And cos of middle vector. So I'm not just writing it. I'm not writing the formula for norm of U, norm of V. Later you can see why I am doing this. Now, you know, we have a formula for A minus B whole square. We can expand the right and left hand side. We are going to expand it. So what we get? So we'll get here then B1 square minus 2A1 B1 plus, okay, it will be basically plus A1 square plus B2 square minus 2A2 B2 plus A2 square plus B3 square minus 2A3 B3 plus A3 square, right? So this side will be what? This side will be same as it is. So A1 square, A2 square plus A3 square plus B1 square, B2 square plus B3 square, right? Minus 2 of norm of U, right? And norm of B of cos theta. So now see one thing, the square term are eliminated from the both sides. So because B1 square is cancelled out by B1 square from this side. Similarly, A1 square, B2 square, A2 square, B3 square, all are cancelled out from both sides because they appearing in the both side with same coefficient. So then the raised term we are getting, that is negative 2 into A1 B1 plus A2 B2 plus A3 B3 is nothing but negative 2 of U vector norm, okay, and V vector norm of cos of middle angle theta. So what we are getting? See, we are getting A1 B1 plus A2 B2 plus A3 B3 equal to U vector norm, V vector norm of cos theta. Now see, this is nothing but the dot product of U with V. Because what was U V dot product? So I have written, I think I have written before. Yeah. This was the dot product A1 B1 A plus A2 B2 plus A3 B3. So what we are getting basically here, that this is nothing but dot product of U with the vector V. So this is nothing but, this is U vector norm and V vector norm of cos theta. So now see, we are happy because this side is the algebraic thing and this side is the geometric thing. So let me write here that so cos theta equals to nothing but U vector dot V vector divided by norm of U vector into norm of V vector. I'm assuming here where U vector is not a zero vector and V vector also not a zero vector. Then we can write this situation. Now look, interesting thing that this side is geometry, the left hand side, and right hand side is algebra basically. So and you have the equality, and this equality we are getting using this actually all step. You know what we have done? First we have written U vector in the component wise, then dot product I defined, and it has some properties. Then if you have two vector, we draw from the initial x point O to vector U and another vector V. Then we getting AB here, this situation. So somehow we are drawing a triangle. You have U vector here, you have V vector here, then AB vector here. Okay. Now then what we have calculated, we calculated AB vector. We have written AB vector using the component of U and V. Okay. This triangle you can draw whatever I have drawn in the screen. That triangle you can draw only for R3 or R2 or the another vector space. I'll tell you, it is not this kind of situation, not possible. And for another kind of situation, you cannot actually define the angle between two vector geometrically, but using the help of algebra you can define the angle between two vectors. Okay, but directly geometrically not possible because you cannot draw the triangle there. So that is my goal. So that's why I give here the connection. So this is nothing but the connection between the geometry and geometric angle and the dot product. Okay, this side totally cos theta is geometrical concept, and the right hand side is the dot product algebraic concept. They are connected. Okay, now see what we can do here, that if so now we have this formula. Now note, this is very important. If U vector perpendicular with V vector, then what happened? And let's say perpendicular with V vector, and of course let's say where U vector both are non-zero, then actually if you put in this formula, perpendicular means the middle angle between two vector, then theta equal to 90 degree. So the dot product will become 0. And it is also the converse true. If you have two non-zero vector, then they are perpendicular if the dot product is 0. Because of this. Because this side is determined by angle actually. And this side is by definition of dot product. Both are equal. Okay. So now see, the cos theta is not defined for any arbitrary vector space, but dot, the concept of dot, you can define for any arbitrary vector space. So dot is nothing but a map from V cross B to the field. You can say to the real field. If we focus on the real vector space, it land to the real. If complex vector space, it land to the complex. So far the concept is basic pre-calculus concept, primary mathematics. It depends on the Euclidean geometry. But this concept, since in arbitrary vector space we have no idea how to draw triangle, this type of situation, this, it is not possible. This kind of situation. So that situation we need to actually identify. Okay, we need to identify the angle algebraically. Okay, that is here basically. The algebraic meaning of angle is nothing but determined by the dot product. And dot product we can easily define for arbitrary vector space. It will be a function from B cross B to the field having some property. Okay, so that I am going to write down here. Now, so one thing here clear that if you take the mode here basically, let me, since I am talking about here, so one thing also clear, we know cos theta mod is always less equal to 1. So this implies u vector dot v vector, this mod is always less equal to norm of u into norm of v. This is called the Cauchy-Squarch inequality. And in R3 we have this relation. So from here we can decide that Cauchy-Squarch inequality holds. But for arbitrary vector space, we cannot write down this expression. So that situation, how we do, totally we have to use the algebraic concept. So let me write down here. So let V is any vector space. V is any vector space. Of course, I am assuming over a real field. In the complex field, you have to little bit change there, but let's say we are assuming everything is a real field over here. Okay, a function, I am writing like this: V cross V to R is called an inner product, or you can say the dot product, or you can say dot product, if it satisfies this property. Let me write here. I'm not say this 1 to 4 all property 1 to 4. Okay, if satisfy 1 to 4 all property. Okay, I have written 1 to 4 mean this equation. This. Now in the place dot, you just denote this notation. So then you will get this. Okay. So then we call it is so a vector space with inner product space. We called a inner product space. So if you have a vector space with a inner product, then we call it is a inner product space. Now in inner product space, we can define the angle between two vectors. Okay. So if V dot is an inner product space, and you take two vector, let's say u vector dot v vector, sorry, u vector v vector from v minus 0 vector, so they are non-zero vector, then angle between u and v is given by the formula cos inverse of u vector dot v vector divided by u vector norm and v vector norm. Now the question is, it is always exist or not? So now it will exist because cos inverse is defined. We know cos inverse x is defined that if and only if the modulus of x is less equal to 1. So now this will be defined if we can guarantee that this is always less equal to 1. And it is yes because of Cauchy-Squarch inequality. So the Cauchy-Squarch inequality, so how it is defined, Cauchy-Squarch inequality tell us that if you take two vectors from the inner product space, take the inner product, then that absolute value is less equal to norm of u into norm of v. Now here, okay, so this is the idea, something like this. Now, okay, now what I am trying to tell you that this Cauchy-Squarch, since this Cauchy-Squarch inequality holds, so this quantity always less equal to 1. So if you take two non-zero vector, there is always a fixed angle theta between 0 to pi actually given by this formula. Okay, because of this is less than always 1. So such a thing exists. Okay. So what we have done basically, we have just generalized the concept of angle from R3 to a arbitrary vector space by using the dot product concept of dot products. So yeah, that's the idea. So in actually in mathematics, what we will do, always we start with a basic problem and try to actually make it is a generalization in the arbitrary mathematical space, like for the higher space. For example, if you start with the real analysis and open interval are very fundamental, that open interval concept you can use and generalize that to study more space, like for example, where you have no such thing like I mean arbitrary space, like you have a set and you can define the concept of openness. Basically, that is the topology you can give on a set. The topology is nothing but collection of some subset having that subset having some properties. Those subset actually generalization of the open set from the R. Okay. So that's why somehow every time what we do, if we have a good concept or good actually problem that we want to generalize. Okay. So this is the whole target in pure math. Okay. So therefore, yeah, that's the idea, and we have seen here one problem that. Thank you so much. So yeah, see you in the next video. Bye.